Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, it's a pleasure to have Sridhar Madhavan here. Sridhar has been working in AI and the area of reinforcement learning for quite some time, has made a lot of very nice contributions to these areas. He's recently been elected a fellow to AAAI, and he's going to give us a talk today on some exciting new developments in RL.
Thanks. So I'm going to talk to you today about some work that actually originated out of looking at problems in reinforcement learning, but the implications of this work stretches far beyond reinforcement learning and includes pretty much all of machine learning. So the main idea I'd like to explain to you is what I believe is a new framework to do machine learning. And it builds on one of the most important foundations of machine learning today, namely optimization. But it takes machine learning well beyond the scope of optimization to something I call equilibration. I'm going to explain to you what that is and why it's going to be extremely important for machine learning to move beyond optimization. Now, when I talk to my colleagues about this, and I've talked to quite a few of them, and I've talked to a lot of smart faculty candidates who have come to UMass, and instinctively the reaction is, what could be more general than optimization? And some people say, well, maybe it's just math, right? The next level of abstraction. And so I want to show you that is not the case. In fact, when you do optimization in machine learning, you are really incorporating some very specific assumptions about the world. And these assumptions are increasingly untenable for the challenges that machine learning faces in our increasingly networked society, in things like cloud computing, the internet, and so on. And so I really want to make the case that the world has changed fundamentally, as all of us know. And so to really grapple with that, we have to really move the intellectual tools of machine learning beyond optimization. Of course, when we talk about optimization in machine learning, we're really interested in not just applying optimization, but we want to scale to very large problems. And so there's this notion that has become popular in work in optimization, particularly convex optimization, which is to get some sort of scale-free property. That is, you want an algorithm that scales incredibly well to high-dimensional problems. And so there's this phrase I'm going to use from a recent overview of optimization by Sebastian Buek at Princeton, almost dimension-free optimization. And I'll explain what that is. But then I'll show you how intriguingly our new results seem to show that this idea applies in this more general setting as well. We understand the sort of fundamentals of why we get this in certain restricted cases for optimization. I think we don't understand very much about equilibration, so it will be a sort of interesting challenge to see why this is happening. So, but before I get there, I want to sort of give you a little bit of background, both into what sort of stuff that people do in machine learning, where does this work come from? In particular, many of you may be familiar with parts of machine learning, but perhaps not reinforcement learning, or you may not be familiar with machine learning at all. So I'm going to cover some background, some history, before I actually get into equilibration. So I'm going to begin with telling you who I am. And I direct the Autonomous Learning Lab at UMass. It's one of the oldest machine learning labs in the country. The lab has been more or less in continuous existence for over 30 years. And we've had a very long and distinguished set of students, postdocs, and visitors. Our first postdoc was someone named Michael Jordan, not the basketball player, famous machine learning researcher at Berkeley, probably the most cited machine learning researcher. He came to us as a psychologist who had not done any work in machine learning. And as legend has it, one day he apparently said, I'm going to learn a little statistics. He breathed the air of Amherst and decided to become a statistician, and the rest is history. So I think Mike set a high standard, and we've had really excellent students. Our first PhD student was Rich Sutton, who is a pioneer in the work in reinforcement learning, who never stopped working on his PhD dissertation. His dissertation was 1984 on temporal difference learning. He has a paper in ICML 2014 on, you guessed it, temporal difference learning, because he really wants to solve this one problem. Most determined researcher I have ever seen in my whole life. So I'm going to talk about his particular solution and why I think ours is better. You can download all the publications that we've done over the past 30 years at this website. We're also part of the School of Computer Science. It's a very long-standing computer science program, and the graduate program that I direct has been in existence for almost 50 years now, so we're proud of it. So this is the lab as it stands now. My lab co-director is Professor Andrew Bartow, or Andy. He retired a couple of years ago, so pretty much I manage the lab on my own. We have a very large number of PhD students. We've always had a large number, about 14 right now, and that's a pretty demanding job. I want to single out 7 students with whom I've done this work: Tommy, CJ, Will, Ian, Steve, Nekpo, and Liu, who's not here. Really, a lot of the work I'm going to talk about are ideas that they get the credit for, and I'm sort of the person presenting them, but the work could just not have been done without these really great students. So let me start with a project that we've started recently to give you a sense of the kind of work that people in machine learning do using optimization before we move on to talk about equilibration. So here's a project that we get funding from NASA and from the National Science Foundation. And what it is we're getting data from a long way away. We're getting data from Curiosity, the rover on Mars. It's a sort of traveling science laboratory, lots of scientific instruments on Curiosity. The specific one we're working on is producing what's called spectroscopic data using a process called laser-induced breakdown spectroscopy, or LIBS. It's basically a very powerful laser, and it can be pointed at rocks, and it pulverizes them. But it's not like Terminator. It produces a very small amount of debris. There's a plasma generated. You can read off the energy, and it produces these kind of readings you see. They're very high dimensional, and it's beamed back to Earth. Now, our problem is to decode what the rover has actually zapped. Now, this sort of men in black picture you see here is me standing with 2 of my students, Tommy and CJ, in Professor Darby Dyar's lab with the identical laser on Earth. So we can zap rocks on Earth to our heart's content, and we can compare the readings we get with those on Mars. So you can think of this as what's called a transfer learning problem, which is we have data from Mars, we have data from Earth, and we have to somehow figure out if what we're seeing on Mars has anything to do with Earth, and what's different. And so this is an interesting machine learning problem, one that has very deep implications for understanding planetary science and whether there ever was life on Mars and so on. So we came up with a new algorithm recently. I won't give you the details of the algorithm, but I'll give you a sense of how it works just to illustrate how we can use optimization to do machine learning on interesting scientific problems. So a very canonical way of thinking of doing machine learning is you take some data and you project it on some well-defined structure and you see what you get. So if you think of canonical methods like least squares, the structure you project on is very simple. It's simply a linear subspace. So you can think of in the dollar sign, this vertical bar would be a linear subspace. You simply project your data on that and see how well the model captures the data. In our case, we're doing something more interesting. We're projecting it on a mixture of spaces. So there's linear spaces like this bar. There's this curved space in the dollar sign. And we have an unknown mixture of these. But each of the spaces that we project on is simple, but they may not be Euclidean. So the idea is we project on these spaces, we see what part of the original data is captured by this, and then we produce a low-dimensional description of the data. This is an example of unsupervised learning. This goes beyond sort of previous work in this area where you could either project on the linear space by itself or one of these nonlinear spaces, but not on an arbitrary mixture of them. And so how do we solve this? We write out this problem as an optimization problem, and I won't give you the details of how that works, except to say that with some cleverness, you can actually make it not just into an arbitrary optimization problem, but something that is actually convex, which basically means we have good ways of solving it. Okay, and the results from the algorithm, which I will not present, are much better than our previous work. So we've actually made some progress here in this. So this is an example of a large number of kind of projects that people are doing in very different applications of machine learning, building an optimization. So clearly optimization is a very useful tool. Why do we want to go beyond it? So I'm going to show you two models, and the one on the left is what we know how to do and what lots of people in machine learning already do, which is optimization. Okay? So we take some problem, like the transfer learning on Mars problem, we construct an objective function, which maybe looks like this. This is a very simple quadratic objective function. To solve this problem, we walk downhill, we minimize the function. Because it's convex, there is a unique minimum. Almost any algorithm you implement will work on this, so it's not very challenging. It's challenging to design a fast algorithm, particularly when the space isn't two-dimensional, but say 1,000,000 dimensions. And particularly when, to walk downhill, you have to know the gradient of the function. And sometimes you can't recover the exact gradient. You can only get a very noisy gradient. So you get a direction that you think the function is decreasing in, but it might not be the right direction. So the uncertainty in computing the gradient can complicate the algorithm, and the number of dimensions could be very large. So even though it's convex, it could be difficult, and so you need some cleverness. But because the problem is inherently well-defined, you can come up with some clever solutions, and I'm going to show you later one such solution. Okay, so we have some function, small f. We're going to minimize this function, and then we're going to find the minimum. Okay, that we know how to do. What's this over there? This is something I assume very few of you have probably seen. This is a new model called an equilibration model. So as the name suggests, it's basically trying to compute some equilibrium solution. And the mathematical origin of this model comes from physics in mechanics. We have some object like a ball sitting on a surface, and you want to find its equilibrium position. Okay? So there's a guy called Stampaccia in Italy who developed the underlying mathematics for this. And the underlying mathematics is called variational inequalities. And interestingly enough, it turned out that it has actually a lot of interesting applications, not just in that original setting, but to a vast number of problems that have subsequently been discovered. And I'm going to show you some of those later in the talk. So in a variational inequality, instead of a small f, you have a capital F. What is the capital F? It's a gradient. In this specific case, it's a gradient. In general, it could be some arbitrary vector field. That means for every point in the space of feasible solutions, capital F returns a vector. So in this particular case, think of capital F as simply the gradient of this function that tells you which way the function increases. In general, capital F, as we'll see, could have many other possible instantiations, okay? So capital F gives us back a vector, and what we're trying to find is some distinguished element x star, at which a certain property is true. Namely, the vector returned by capital F makes an acute angle between 0 and 90, with all vectors of the form x minus x star, where x is part of the feasible set. Now, if you're like me and you see this for the first time, it makes no sense whatsoever. Okay, what does this mean? And so I'm going to explain that to you later. But here's the interesting part. Every problem that we can write like this turns into a problem like that. That's interesting. Lots of problems that we can write like equilibration cannot be turned back into optimization. So it's strictly more general. And I'm going to show you two things. One, I'll take a problem that we know how to solve with optimization, or we're trying hard to solve with optimization, and I'll show you why, if we move to equilibration, we can solve it better. That's the reinforcement learning part that I'll show. And then I'll move to the equilibration part and show you lots of interesting things that we can do now that we understand better how to do equilibration. So that's the plan for the talk. But after I did all that, I said, it's not interesting enough. So you still don't know who I am, right? So I have to tell you a story. When I teach the machine learning class, I tell stories. And what happens at the end is the students don't remember much machine learning, but they remember all my stories. And I figured some good comes out of that at the end, and they actually remember perhaps even more than I think they remember. And so you're going to get some stories, okay? So who am I? Where did I come from? Why did I do any of this? And so on, right? So when you become a scientist, there's usually somebody who's a big influence on your life, right? It varies. Different people have come into science for all kinds of reasons. In my case, it was my dad. So here's my dad. And he's actually an archaeologist, a very special kind of archaeologist. He deciphers ancient languages, or tries to. And one of the languages that he's actually successfully deciphered is this language. It's called Tamil. It's a very old language, but spoken by about 100 million people in the south of India. That's his name, Airavatham Mahadevan, written in Tamil. It's a very pretty script. The one he actually deciphered is the one on the right. This is Tamil as it was written in the 5th century BC. So they were writing all over the caves in the south of India that nobody could read because they didn't know what it meant. And my dad sort of got interested in this and said, oh, that sounds like an interesting problem. He was actually not supposed to be doing this. He was working for the Indian government, but that didn't seem to take up very much of his brain. So in his spare time, he decided to dabble in this, and he got hooked. So, and he's worked on it a long time, but he wrote a very monumental book that was published by Harvard University Oriental Series. Professor Michael Witzel at Harvard, who's the Wales professor of Sanskrit, is the editor, and that's the book. It's a very impressive book. Now, what's impressive about this is that my dad is not a university professor. He has no college degree. He never successfully finished a degree. All of this is done in his spare time. So it's impressive that someone who simply dabbles in this can produce a scholarly work that Harvard University Oriental Series considers it worthy to publish. This is the first impressive thing about my dad. So as you can see, it made a big influence on me. Now, my dad himself was motivated. That's my dad 2 weeks ago, very proudly holding the second edition of his book. He himself was greatly influenced by Professor Eminow, who founded the linguistics department at Berkeley and lived to be 101 and was publishing papers till 100. So I wish my dad a long life and hope he lives to 100 and publishes papers. Each year, he seems to write more papers than I do with no NSF funding and no grad students. So that's interesting. Okay, so the other problem that my dad worked on is the Indus script. Now, this is a mystery. This is an ancient civilization that flourished 2,500 BC, and we have data from the civilization in the form of these tablets. Nobody knows what they mean. Well, 50 claims of decipherment have been made. None of them agree. We don't know what it means. We have this text. We can try to parse it. There are lots of theories about what it could possibly mean. Nobody knows. So my dad says he finally has figured it out after 40 years, and he's writing a 100-page paper on it. I wish him the best of luck. But you can ask, can machine learning solve this problem? And my dad has been telling me for a while, you know, you do machine learning, why can't you help me? Like a good son, I should have listened to him, but I didn't. My colleague at University of Washington, Rajesh Rao, did listen to my dad and wrote a paper that I should have written in Science. What did they do? Well, some people said, including Professor Witzel at Harvard, maybe this is not a language. Maybe we're misreading this whole thing. It's business correspondence in some ancient shorthand, but it's not a language. How would you check? Now, this is a problem that machine learning can address, and so this is the paper they wrote. It's a very simple idea. It appeared in Science. Well, if it's language, it should compress like language. That seems logical. So they took long sequences of different length. They computed what's called the entropy, which is simply how well does it compress. They compared the entropy of IndoScript's text to lots of known languages, ancient and modern. And they compared it to entropy of DNA sequences of similar length and Fortran code. And what did they find? Well, Fortran code, as we know, is very, very structured, compresses extremely well, better than any language, no surprise. DNA is not completely random, but much more random, doesn't compress well. But IndoScript compresses like pretty much most languages. That's...
So that wasn't the hypothesis, right? The hypothesis was the business transactions. So.
Right, but this is basically saying, look, it compresses like language, so maybe it's language. Now, this has, of course, raised a lot of controversy, and people said, well, is this a true test? I don't know. It looks pretty compelling to me, but I think it's interesting. This is something that machine learning can do. Okay, so that's a little aside. Now, this is a very nice saying by William of Ockham, which has a lot of influence in machine learning, which is, in Latin, it means do not multiply entities unnecessarily. It's rather crudely translated these days as Occam's razor, a phrase I just do not like. Because first, it doesn't mention that William said it. It mentions Ockham. Ockham is just a town near Surrey. Who cares? Second, it's sort of, actually, we don't really know what William said, but this is what Bertrand Russell said William said. So we'll assume that this is correct. So we're going to use this as a criterion, right? We want things to be simple and beautiful. All right, so why should machines learn? Let's start and answer this question really quickly. So when I was at Carnegie Mellon, my advisor was Tom Mitchell, and I was sort of there as a visiting grad student because he had just moved there and I was finishing up. So I spent 3 years at Carnegie Mellon, and I listened to a lot of wonderful lectures by Herb Simon, a Nobel laureate in economics, who was very interested in psychology, computer science, machine learning, AI, and so on. And he asked this question, why should machines learn? We can just program them. Why should we bother learning? Humans learn because it's very painful to program them, but it takes forever for them to learn anything, as anyone like me will tell you who teaches for a living. But he came up with this nice definition of learning, which is very useful, right? So learning is changes in a system that are adaptive so that it helps the system do the same task better the next time around. We're going to use this definition. So why should machines learn? Can we think of an example? So when I graduated, I went to IBM Watson Research. In 1990, they did not have a machine learning group. Those days, it was not clear whether machine learning was good for anything, unlike today. And so they threw me in with a new robotics group that they just formed, but I knew no robotics. 2 years later, I produced this book, and it went on to be quite influential. And Shyam mentioned my AAAI fellowship nomination, and I was sort of gratified that I was being nominated in part for the work that I did at IBM all those years ago, because it was the first book of its kind on robot learning, which has since become a major area. So I'm going to use this to motivate the reinforcement learning problem and show you how we solved it with equilibration. So in the reinforcement learning problem, we have the problem of teaching something how to do a task like this. Now, the way this task was solved in the book described by Dean Pomerleau, who did it, was they constructed a neural net that took samples from human drivers driving a real Ford truck, input images and an output of the steering command, and they trained the neural net. And it was the first demonstration that machine learning could drive a truck. And this was impressive because the work before this on NavLab was humans programming this truck using state-of-the-art computer vision in those days, and they had failed. And the truck was barely moving with computer vision. But with machine learning, it could drive at 60 miles an hour. So it was very impressive. So here's an answer to Simon's question. machines can do things by learning that they couldn't do by programming. Of course, now we know how to program machines to drive, and Google's putting a lot of money into this, so the world has changed. But we don't solve the driving problem this way. We solve the driving problem in a different way. We sort of learn to solve driving by solving a sequential decision problem. And I'm going to use this phrase by a famous Danish philosopher, Kierkegaard. And he says, life must be lived going forwards, but can only be understood going backwards. So what does that mean? This is the essence of the solution to the driving problem. How? So let's look at the first machine learning program that was ever built. This is by Samuel. Many people in my machine learning class have no idea who Samuel is, so here's a history lesson. Arthur Samuel was a researcher at IBM who built the first machine learning program ever, demonstrated in 1956 on PBS. This is a photograph of the PBS show, where the computer is playing a game of checkers. And you have to realize how revolutionary this was. 1956, people were using computers to build atomic weapons, largely, after the Second World War. Nobody knew computers were good for anything else. The president of IBM, T.J. Watson, said he thought the world needed 5 computers. That's it. He didn't think there was any need for computers beyond 5. And of course, this was a wake-up call. And T.J. Watson said, oh, this is going to raise the price of IBM stock by 10 points on Wall Street that day. And it did. Because all of a sudden, people said, wow, machine learning, computers can do interesting everyday things. But what was truly impressive was it learned to play on its own. There was no teacher. How did Samuel figure this out? So he used this algorithm called temporal difference learning, which my colleagues at UMass, Andy Bartow, and his former student Richard Sutton, have done a wonderful job studying over the past 3 decades, and written this beautiful book on reinforcement learning, which has been cited quite a lot, and has had a lot of influence in many fields. And I'm going to briefly explain to you how TD learning works, why the original algorithm wasn't quite right, and why equilibration led to its solution. So let me contrast the way TD learning works with least squares. Let's take a very simple problem from the book, a problem that we all solve every day. Let's say I'm going home, and I need to make sure I get home on time. So I leave my office, and I think, oh, maybe I'm going to take half an hour to get home. And I'm going to make sure that I reach in time because my wife has told me that dinner with our neighbors is at this time, and you better not be late, as usual. So I say, okay, I'm going to take half an hour, I start home. And then somewhere along the way, I run into a colleague, I start talking to him, and by the time I get to my car, I think, oops, it's going to take longer. Maybe I'm going to take 40 minutes to get home. And then I start driving, there's less traffic on the highway than I thought, and then I realize, oh, it's not going to take me that long, maybe 35 minutes. I keep revising my estimate, eventually I get home, and I know exactly how long it took me. Imagine you're doing this over and over and over again. Well, you get the error signal between your predictions at every point and the final outcome, and you do least squares. Well, but you shouldn't solve the problem this way. You should solve it using TD learning, which gives you the error signal right away. But every time I teach the machine learning class, I ask the students, how would you solve this problem by getting the error signal right away? And nobody ever cracks that unless they know the solution already. So it's just a really non-trivial step. So TD learning compares the errors over successive steps. So you set 30 minutes in the beginning, then you revise your guess to 40. It says, oh, there's a difference of 10. I can learn from that. But that's crazy because that 40 was a guess too. Still it works. That's the amazing part because it turns out that original error signal from 30 to the actual time can be decomposed into the sum of temporally successive errors. So part of that error signal is already available to you at the next time step. You don't have to wait till the end. This is the genius behind temporal difference learning used by Samuel and by many other people. The beauty of TD learning, it's a simple algorithm. You don't need an advanced degree in math or statistics to implement it. A high school student can implement it and have. So it's beautiful and it's simple. Is it true? How do we ask this question? Yes?
Just a stupid question. What is the problem we are trying to solve with this?
We are trying to predict. In this particular example, we're trying to predict how long it's going to take us to get home. So at every point in time, like I'm in my office, I reach my car, I'm on the highway, I'm on another highway, I'm getting closer to home. When am I getting home? So that I have to make sure that I have an accurate sense of how long it's going to take me to get home. This is an example, right? For checkers, it would be, what is the best move I have to make here? All of these are sequential decision problems.
Something where information is being revealed to you gradually.
That's correct. So at every point you observe the state of the world and you have to make a prediction. And
It's like a martingale or
yes, that's correct. You can think of it as a martingale. But you don't have the outcome, like, for example, how long did it actually take me, or did I win the game or lose the game, until the end. But you still want to learn even though you don't know the actual outcome. That's the difficult part. Right? And TD learning shows you how to solve that problem. And the reason it's important is because many, many problems that we solve every day as human beings, as animals, involve sequential decision. That's Kierkegaard's statement. We live in the world, data comes to us sequentially, the world reveals to us information sequentially. That's the only way we can actually learn, because we don't have a huge table that somebody stored in a database that we can process. The data comes to us sequentially. So it's an important problem for us to solve. Yes, you had another question.
In what sense are the two graphs denoting different learning algorithms? It sounds like the predictions are the same at the different points of time.
But the error signal is completely different. In one case, you're comparing your prediction at each time with the final outcome. In the other case, you're comparing your prediction each time with the prediction you made at the next time step. So you're learning from a completely different error signal, whatever the underlying machine learning technology is.
so you have a better estimate of your error. Maybe your prediction is the same, but in the second situation, you have a better estimate of how accurate is your prediction.
Well, in the second case, you're getting your error signal right away. You don't have to wait. Maybe it takes you 5 hours to get home. In the first one, you have to wait 5 hours. You're not learning anything. Right? In the second one, you're learning at every time step, which is the real improvement. Okay, so, but does this work? Is this really right? Now, the neuroscientists are all excited because they have lots of data showing the brain actually does compute TD signals. I won't go through this literature, but this is the analysis. Unfortunately, TD learning does not work. It's not a gradient method, so we can construct really simple problems where if you look at the weights, they diverge. So you run the TD algorithm, the weights simply blow up. This has been known for 30 years. How do we solve it? Well, the way we solve it is we make it an optimization algorithm, right? We do gradient descent. So we have to come up with the gradient method, like least squares, where we write out an objective function, do gradient descent, and we can be sure we might not find the optimal solution, but we'll find a stable solution, a locally optimal solution. Unfortunately, all attempts to do this over 30 years have not met with success. The most recent attempt was Rich Sutton's work, where he tried to do this, and he came close, but I would say not quite right, because the final algorithm is not a gradient algorithm. And so this is the solution we came up with. It's described in a very long paper that I cannot explain here, sorry, unfortunately. It's a 126-page paper written with 7 PhD students on archive. The paper is long because we actually showed that the solution works not just to fix TD learning, but solves a variety of other problems in reinforcement learning as well. It gives us sparsity, scalability, safety, and reliability. But I'll just focus on the TD learning part before I move to equilibration. So how do we modify Kierkegaard? We say, life can be only understood by going backwards in the dual space. What does that mean? So let's understand how to do dimension-free optimization. So we're going to use this cute trick by 2 Russians, Nemirovsky and Yudin, called mirror maps or mirror descent. They developed this in the 80s, but the book was obscure. Nobody understood what they were talking about till about 2000, when it became clear. So here what you do is you don't do gradients in the original space. You map to a dual space and do gradients in the dual space. If you do that, they showed you get very nice properties. We're going to use this trick. Now, I won't go into the details of how to map into the gradient space, except to say, roughly, what you do is you find a suitable function, like a strongly convex function, you compute its gradient, and that's a one-to-one coordinate transformation on your original space, and you pretend that that's your new space. Now, by choosing that function carefully, you can get lots of nice properties. So that's what we do in our long paper. Now we come to the heart of the new framework. What is a variational inequality? Okay? So we have a feasible set, just like optimization. We have to find, and we have this vector field mapping. Every point in the set, it points in a different direction. We have to find the distinguished element x star at which one property is true. What is that property? The vector f, the vector field f at x star points in such a way that every vector of the form x minus x star forms an acute angle with it, an angle between 0 and 90. Another way of saying it is, if I go in the direction f of x star, but the negative f of x star, I project outside the set, and if I go backwards, so if I go from here, x star, go in the direction minus f of x star, I get outside the feasible set. Because the feasible set is convex, if I project back, I should come back to the same place. In other words, it's a fixed point. If that's true, I found the solution to the variational inequality. Okay? You have to trust me that this generalizes optimization. Every optimization problem can be written this way. Now, unfortunately, you can't do gradients here. You can try a gradient method, it's not very good, but this is another cute trick. It's called the Extragradient Method, and this solves variational inequalities very nicely. How does it work? So remember, we have to find this point at which if I go outside the set and I come back, I'm in the same place, right? So here's a very simple idea. Start somewhere. I don't know if I found the solution. Let's go in the negative f direction. Project back. Oops, I'm in the wrong place because I'm in a different place. Now you can imagine keeping on doing that. That turns out to be a very simple algorithm. It doesn't work quite as well. What Extragradient does is says, okay, what you do is now at this new point, again project in the negative f direction. That gives you maybe this direction. Now go back to the original point and imagine this was the direction at the next step. It wasn't. It was the direction of the next step beyond that. But so this is what Extragradient does. It's a clever idea. So you can combine these two ideas and you get this algorithm called mirror-prox, recently published by Nemirovsky. And what does it do? It does gradients, not gradients in the dual space, but extra gradients in the dual space. Okay, so 2 steps. Don't do gradients here, do gradients here. And in fact, don't do gradients there, do extra gradients. And if you do all of that, here's a solution to the temporal difference learning problem, which is 2 changes. First, you should do extra gradients, and you should do extra gradients in the dual space. Now, my lab co-director, Andy Bartow, looks at this and says, what have you done to my temporal difference learning algorithm? It's not pretty anymore. But the question is, does it work better? And we claim it does. And very quick examples. In the Baird example, this is the latest version of the revised gradient TD algorithm by Rich Sutton. And it doesn't blow up, but the variance is very large, and it has very slow convergence. This is our modification using extra gradients. And you can see the variance is much, much smaller, and the convergence is much faster on the same problem. And in fact, we can prove, and we do that in the paper, that theoretically also our bounds are much tighter. Here's a robot example where we show much better performance on a 20-dimensional robot arm using our new method. And finally, in our long paper, yes?
Yeah, so if you're doing kind of gradient, do you have a target function that you're trying to minimize?
Yes, so this particular one, we use the mean square projected Bellman error. Remember, we're still doing optimization here, where we're using VIs to solve optimization problems. So finally, in our long paper, we show lots of other advantages for this approach, one of which is we can do reinforcement learning on robots in a safe way. Namely, you can say, I have this very expensive robot. I want to make sure it doesn't fall over. And I'm going to tell you parts of the space that when you're learning, you should never visit. And we can guarantee that. And how do we do that? We discovered that people who've been programming robots with machine learning algorithms, reinforcement learning algorithms, were using this algorithm called natural gradient, popularized by somebody in Japan called Amari. And I won't go through the details of how it works. But we discovered an interesting mirror map that makes this algorithm a special case of mirror descent. Unbelievably, in the last 30 years, nobody had seen this. And once we discovered that, and it's published in last year's NIPS, then it was very straightforward to modify the mirror descent algorithm that we had come up with to make natural gradient safe, and that's what we showed that you can do. Okay, so that's basically saying that the framework of variational inequalities, equilibration, helps you take optimization problems that are long-standing and solve them without even considering problems that are beyond optimization. But that's part of the story, why we should consider this new framework. The second part of the story is it opens up a completely new frontier for machine learning. It gives us access to problems that we can't solve now. And that's why we should do it. So let's see what those kinds of problems are. So we're all aware of the huge influence of the internet on our lives. And lots of people have said interesting things about the internet, but basically the internet is like the free market system. It isn't designed by one person. There are lots of competing forces that shape the internet. And so you can think of this sort of interesting way of thinking about the internet, the invisible hand of the internet. Invisible hand is a famous phrase of Adam Smith, who founded economics a long time ago, and basically saying it works in a sort of mysterious way. Everybody's doing their own thing, but somehow the whole system works. And it took economists quite a while to sort of show that Adam Smith was largely correct under certain conditions. And much the same is being used today to model the internet. Lots of interesting work in algorithmic game theory, things like selfish routing, where people are trying to understand how is it that we can have these competitive forces work and still produce common good on the internet. My claim is that if you're going to sort of realize that the future of machine learning is just tied up to the internet, all our data is coming over the web, you have to move away from optimization to an equilibration model because there is no single objective function. And I'm going to show you that in a series of examples. Okay? So, I was listening to the BBC at 5 o'clock in the morning about a week ago, and they talked about this interesting workshop called Hack in the Box, about how sort of the internet has just totally changed from its design 10, 20 years ago, and we have all kinds of competing things like net neutrality, security, privacy. I mean, all these competing forces shaping the design of the internet. And so we're faced with this reality that there isn't no single way to model lots of things we want to do on the web. And so it's very difficult to think of solving interesting problems on the internet purely by writing down an objective function like we do in optimization. What we have to realize is there are going to be competing forces. They're all going to be optimizing their own things. And the best we can hope to do is achieve an equilibrium solution. The question is how to do that in a nice way where we preserve some interesting properties, and it's not just ad hoc. And that's what variational inequalities gives you. So here's a story from LA Times recently, where Verizon is telling Netflix to stop blaming it for streaming issues. And I'm going to show you that this is entirely predictable from our model. Okay? This is exactly what you'd expect to see. Because Verizon is basically saying, well, don't blame us. If your customers are having trouble accessing our movies, or basically like you're not routing things correctly. And Netflix is telling Verizon, we're not routing because you're kind of not doing what you're supposed to be doing, and they're playing a blame each other game. And this is because they're competing in a different way, and they're sort of optimizing different goals. You can't sort of take the standard machine learning approach here and say, well, you know what, let's write out a loss function where we do a linear combination of the goals of Netflix and the goals of Verizon. It's not going to work. We can't solve this problem this way. We have to realize that we're beyond what optimization can do here. So how do we solve this problem? Okay, and it's a story that I can't tell you in full detail, but I'll give you a sense of how the solution arrives. So the first thing to realize is by moving to variational inequalities, you are able to sort of model a great variety of other problems. So you can solve sort of all the standard non-cooperative game problems that people study in algorithmic game theory, in selfish routing, in areas like that. You can solve problems that are called complementarity problems, network equilibrium problems, and other things. So all of a sudden, if you solve a variational inequality, like using extragradient or something fancier, all of these problems become accessible to machine learning, and they're not now if you use simple gradient methods or convex optimization methods, unless you make huge assumptions, like, for example, your Jacobians are symmetric, or various other things like that, which are simply not true for these more complicated problems. So how do we go from dimension-free optimization almost to almost dimension-free equilibration? So we need an equivalent equilibration algorithm which has these nice properties. And unfortunately, extragradient is not that method. Okay? So let's go back and understand a little bit about how this works, right? So we start here, we go in the negative f direction, project back. If you're at a fixed point, we're done. That's extragradient. So extragradient takes these two steps and solves it. But unfortunately, it doesn't guarantee or doesn't really show, and I'll show you some results that get at this. How do we go beyond this? All right? So here's our final modification of Kierkegaard. So what we say is life must be lived going forwards many times in the dual space, but can only be understood by going backwards many times in the dual space. That's going to sound like philosophy, but it works. And here's the algorithm. I won't really try to explain it. It's a little complicated.
Didn't like the primal space.
So now we're going to do this sort of clever modification of mirror descent by bringing into it an old idea from solving ordinary differential equations. It's called the Runge-Kutta family of methods. And we're now applying Runge-Kutta methods with mirror descent, not on a function that you're optimizing or minimizing. We're applying it on these F mappings, the vector field mappings that are in variational inequalities. And basically, we do a bunch of things like that to make this work. But rather than give you the algorithm, I'll give you results. First, you can do very simple benchmark problems. And here's one. Here's a mapping where the mapping is affine, but it's non-symmetric. So you can't solve this as optimization. So this is your vector field. And this is ax plus b. That's A. And you have to solve it. And here's our results. Very briefly, this is our Runge-Kutta method of a certain order, 5. And as we increase the dimension, the number of iterations to convergence is pretty flat. So it looks promising. But this is a simple problem. Let's bump it up a little. Here's an interesting model of the next generation of the internet proposed by a colleague of mine at UMass, Anna Nagurny, who's actually one of the world's experts on variational inequalities. This paper recently won a Best Paper Award at an ACM conference on the internet. So in this model, what you have is service providers like Netflix, Amazon, Hulu, and so on, playing an interesting kind of game. It's called a Cournot-Nash game, where they're competing primarily on the basis of quantity. They're like the OPEC oil producers who don't set prices, but they set quantity. And then you have the network providers like Verizon, AT&T, competing on prices. And you have users in demand markets like Cambridge, and so on, who are choosing between combinations of content and transport. This cannot be solved as optimization because there are lots of competing forces going on, but you can solve it as a variational inequality. And I won't get through the details of the model. It's kind of complicated. And you can look at the original paper. There are lots of equations which describe the full model. But you can look at simple examples. For example, let's take two service providers, a network provider, a demand market. And you can pretty much work out by hand, actually, what the model should compute. And you get things that economists actually model a lot. For example, what does it cost to produce content? What does users willing to pay? What are the transportation costs, opportunity costs, and so on and so forth? It's a very elaborate model. And you can show the results. The results are basically how much content is flowing from a particular content provider to a particular transport provider to a particular demand market. Okay, so this is roughly how the model works. Here's our algorithm. So what it's showing here is the number of iterations to convergence. We're comparing against extragradient. And here's our algorithm, which is much better behaved over a fairly large zone. So it seems like we're getting something like almost dimension-free convergence, because the number of iterations is not going way up. Here's another problem we just recently did. This is a large supply chain problem which is sustainable. And here, our results are even more intriguing. Basically, this is supply chains are, you order an iPad from Apple, and a week later, it comes all the way from China to your doorstep. It's an amazing supply chain that Apple has set up. This particular one is interesting because it tries to model how supply chains could be sustainable. So these are two examples that are drawn from 20 years of work on network equilibrium problems. So there's a vast number of interesting problems that we can now go after using the tools of machine learning. And here's our results. Look at our algorithm over 4 orders of magnitude, from problem of size 100 to problem of size 1,000,000. Number of iterations does not change. It's pretty much converging about the same rate. Now, when I saw this, I was like really excited, but I can't explain why this is happening. I sincerely hope it's not a bug in the code, but We've run it several times. And so our task is to figure out exactly what is going on here, theoretically, to understand why we're getting this scale-free behavior. Of course, we're building on ideas from the optimization setting that have similar properties, so perhaps they're carrying over in this richer setting. And this is what we're going to explore. Okay? So, to conclude, what I've shown you is a new framework for doing machine learning that starts by moving away from optimization to this more richer framework of equilibration. The underlying mathematics builds on this idea of variational inequalities, where we're given a vector field and we're given a feasible set, and we have to satisfy a certain property. It turns out every problem here can be written as a problem here, but then problems here cover many other things for which you can't really solve them as traditional optimization problems. So this is, I think, a beginning of a new frontier for machine learning, one that opens up lots of interesting real-world applications of interest to many people in computer science, including things like cloud computing and the internet and many other things. So let me stop here. Thank you. Yes?
Isn't solving a variational inequality an optimization problem?
No.
Why?
Well, so when you say you're solving an optimization problem, you have to define what do you mean by optimization. So when you write an optimization problem, you have an objective function in mind. You're minimizing something. There is no objective function in a variational inequality. You're not minimizing anything.
Holds and zero otherwise? Zero if the equality
Yeah, but that's not a minimization problem. That's saying, find me an object with this property. That is not optimization. Optimization means that you have to have a sense of progress. You're minimizing something, right? So you can take a non-convex problem or a convex problem. They turn into VIs, but there are VIs that don't turn into optimization problems unless you have special properties. So for example, if the vector field mapping has a symmetric Jacobian, you can show that there's an equivalent optimization problem. But almost always in real-world applications, that is not the case. Something that economists actually who work in this area realized 20 years ago, that you can't solve. For example, let's take the traffic equilibrium problem. Every time, I've sort of driven into Boston this semester maybe a dozen times, and every time I come to Cambridge, I'm a bigger and bigger believer in equilibration because of Boston traffic. And if you look at network congestion, traffic equilibrium problems, you really don't want to model them as optimization problems because you have lots of users sharing a space, you have network congestion or road congestion, and that's why people who study the economics of traffic equilibria have given up on optimization 20 years ago. They know this is not the way to solve the problem, and that's why the theory of variational inequalities has been really richly developed by these folks. Yes, so one way to think about it is that when you're solving a problem like this, you have many different goals, and there isn't a sort of way of saying, I can take all of them and linearly combine them, because that doesn't make sense.
There is no, the easy point is that there is no unique, when you say optimization, you mean convex optimization, so and in equilibration there is no unique optimum that you're looking for. That's the point, because there are many equilibriums. Or?
Well, so if you think of, say, non-cooperative games, so that is a special case of a variational inequality where suddenly the property you're talking about is true. In other words, when I solve a non-cooperative game, I'm trying to find, say, for example, a Nash equilibrium, and there could be multiple Nash equilibria. There's no notion of optimization in a non-cooperative game. But you have to remember, a non-cooperative game is a special case of a variational inequality. So variational inequality tries to abstract that property of the fact that there is no unique solution in an optimization sense, only an equilibrium solution, but it abstracts that to lots of other problems where similar properties are true. Now, the property that optimization problems convert to VIs is true whether you're doing convex or non-convex. It has nothing to do with convexity. However, if you have a convex optimization problem, it turns out it turns into what's called a monotonic VI. And because the F mapping is what's called a monotone operator. And so one way to understand variational inequalities is that it is the nicest generalization of convex optimization that preserves all the nice properties of convexity. Okay. So in other words, you get, if you had convexity to begin with, then you get the equivalent nice property in the VI setting, but you don't need to have convexity. Now, that doesn't mean that VIs are easy to solve. There are cases where VIs are extremely difficult to solve because you have a richer space of things. But you go find special cases. It's whenever you start with a framework that's more richer, you get more sort of challenges computationally, which I think this is why this is wonderful machine learning, because we love challenges, right? We want to solve hard problems. We want to find where machine learning can really help. And I think, anyway, that's my hypothesis.
Another question, you can just have Team Cookies outside. We can ask Sridhar questions there.
Great, thank you very much.